of the solar system: asteroids, meteors, and of course, comets. All right. When you look at a comet and when you look at an asteroid, the differences are quite clear, right? You have comets in here, different type of comets. We can analyze a comet by looking at the nucleus of the comet, and then you're looking at the jets that are being released as they approach the sun. Now, the comet's tail, right, is not necessarily as short as you see in this picture here, right? This is a Hayakutake comet, by the way, from 1996. It was on all over the news. I remember I was still a kid back then, but I remember it was quite a thing because people were we were able to observe it, right? It orbit the sun, and it actually partially vaporized as it passed near the sun. Right? Now, the thing about the comet tails is that you see it can be of millions of kilometers of length, right? And the thing about the comet is that it has actually two tails, right? We have the dust tail, which is the one that you expect as the comet orbits the sun. The comet is mostly made of ice and rock. So the ice will melt as it approaches the sun, and then you will have this tail. But then you have this ionization tail, which is normally of bluish color, blue ions, excited ions. And why is that? Because the comet, which has a hydrogen envelope, you have ions surrounding this, charged ions, which are going to be pushed to the side by radiation pressure from the sun. Any object or any sort of mass, right? In this case, ions will be will feel a force due to the not the gravitational force of the sun, but radiation pressure. You see, the sun emits electromagnetic waves, and electromagnetic waves carries energy and momentum. Energy makes sense, it's radiation. Momentum is a bit more tricky to understand because we're talking about a wave, but you're also talking about particles, in this case, photons, which are propagated at the speed of light. And they are massless. So how do they have momentum? Well, any particle has an associated wavelength. The associated wavelength we can use to compute the momentum by using the de Broglie equation, h divided by lambda, which lambda is the wavelength of an associated, in this case, associated particle. So we can find the wavelength of a subatomic particle or a fundamental particle. And we can actually use that to explain how this momentum, which is related to the force equals to change of momentum, according to classical physics, right? Newton physics. So we can prove that if there is a change of momentum, there is a force. If there is a force, there is pressure. So that's what we have the ionization tail, which again is very, very long, right? This one is of 150 million kilometers, so about 1 AU of length. We have found comets which have tails of about a few dozens of light years long. So that's how long the tail of a comet can be, which again, that explains why they are easily to be visualized, to be found, right? So it's easier for us to track the orbit of comets, right? Because of their composition, because of their tail, right? Because of the visible light that they emit, right? And then when we look at comets' orbits, we see that they have a very highly eccentric orbit, meaning they have a very elliptical orbit. As they approach the sun, you can easily see sort of like a slingshot type of pattern in here, right? Again, remember, as the comet approaches the sun, at the perihelion, it has its maximum speed. The closer an object is to the sun, the faster it moves, right? So it gains kinetic energy by the slingshot event, right? The slingshot event, or the slingshot idea in physics, is the idea of an object, in this case a comet, exchanging gravitational potential energy into kinetic energy as the object approaches the sun. So you can use the gravitational pull of the sun to accelerate its orbit. So that's why it does this type of shape, which in some cases it looks like a parabola, right? But if you look at it closely, more closely, then you can see this elliptical orbit. So if you compare it with the orbits of the other planets, you can see how different this eccentricity is to the eccentricity, for example, of the Earth orbit around the sun, which is fairly circular, right? So you can say that, for example, exploring and investigating the orbit of the Halley comet allowed Newton to corroborate its Newton's laws and to corroborate the ellipticity of the orbit of planets, right? Remember, it was Kepler who suggested that the orbit of any object orbiting the sun was in elliptical fashion. There was no math, however, to prove that. The math came by using Newton's equations, right? If you apply force equals to mass times acceleration, you get a differential equation. And then using calculus, you get the equation of an ellipse. Okay, and the equation of an ellipse can be used to model the orbit of comets and therefore planets which orbit the sun, and of course moons and asteroids. Okay, so to explain meteor showers, which many of you have heard about, for example, the Gemini, right, meteor shower, we need to use comets, because the thing about meteor showers is not well, yeah, it's meteors, because the thing about a meteor, by the way, is objects that are entering the atmosphere of the Earth, but then they are vaporized. So they never reach the surface of the planet, right? That's a meteor. A meteorite, with TE at the end, is a rocky object that enters the planet, and it survives that disintegration and it strikes the ground. And then you have the meteorite with ID at the end. It's just smaller asteroids, rocky objects orbiting the sun. Asteroids are actually large rocky bodies orbiting the sun, and normally we find them in between the orbits of Mars and Jupiter. Can they be scattered and move out of orbit? Yes. And that is what makes asteroids more dangerous than comets, because they have this irregular behavior by these collisions in the asteroid belt, and they don't emit light. They are very obscure. They don't have a tail. So it's hard to track them, which is why NASA has a whole program to track near-Earth objects, right? If you type this, you have Earth close approaches. If you go to NASA, they have a whole catalog here, and you can filter the catalog by recent objects, future only, by the distance, by a limit, Hubble limit in there, and then of course distance, normally you want AUs, and then you have here, right? And they are updated every day. Look, for example, this one was today, right? And it gives you the eccentricity, very high eccentricity, right? It gives you the node, the perihelion, the period of orbit, right? its absolute magnitude. And look at the absolute magnitude. That's actually interesting, right? The absolute magnitude is very high, which is telling you that it's a very obscure object. The higher the absolute magnitude of an object, the lesser intensity of luminosity it has. And the brightness, right? It will be less bright in the night sky, right? So obviously, like the sun, for example, have apparent magnitudes of -20 and absolute magnitudes of negative values. I don't remember exactly the absolute value of the sun, and the full moon as well, right? They have the magnitude is what you guys see in a stellarium, by the way. Okay, the lower the magnitude, the more brightness. The absolute magnitude, however, is related to the intrinsic brightness of an object. In this case, of this near Earth object. All right. So that's what we have this catalog. All right. Oh, not that. So when comets break down, you have a tail. Now, if the tail is very big, right? Chances are, as the comets orbit the sun, they have a period. So every year, a comet with a very long tail may intersect the orbit of the Earth. That's when you have your meteor showers. That's why we have meteor showers every year, depending on, around November, sometimes in September, sometimes in December, sometimes in April. It depends which comet is approaching the sun at that point. Okay? So that's the explanation behind meteor showers. Now, when you look at the origins of comets, why do they approach the sun? Remember that there are two places where they originate. We have the Kuiper belt, which are all these icy objects beyond the orbit of Neptune, which is very flattish, by the way. Look at this. That's where Pluto is located. Look at that. So Pluto intersects the Kuiper belt. And then you have the Oort cloud, which is a more spherical cloud of icy objects way beyond the orbit of Pluto, in the boundaries of the solar system. Okay. So these are the two places where we can find icy objects that eventually become comets. Okay. So there it is, right? That's kind of what happens when a comet in highly elliptical orbit moves towards the sun. Sometimes it can be disturbed by the gravitational pull of other planets. For example, Jovian planets, right? They have a very large mass. So if the comet comes close to a Jovian planet like Saturn or Jupiter, then it can deflect the comet. Sometimes the comet can be deflected towards the Jovian planet. For example, the Shoemaker-Levy, which was deflected towards Jupiter, right? Sometimes it can be deflected away from the sun. Now, what happens sometimes is that a comet may crash with the asteroid belt. And that's a perturbation that we have to be careful, because sometimes a comet may interact with the asteroid belt and may bring some of those asteroids out of orbit. And those asteroids are quite close from the Earth. So we have to always look closely what happens then, because some of those asteroids may be small enough so nothing will happen, may be in orbit towards the Earth. Now, we know that asteroids pass very close to Earth orbit around the sun. And this happens every day, by the way. And throughout human history, we've been lucky that we haven't had a large asteroid hitting the Earth, at least in the past several thousand years. And we can even go back to the dinosaurs, right? 65 million years ago. However, you could claim that we have had very close approaches. And you can also claim that we have had encounters or situations like the Tunguska event. You don't know, the Tunguska event, what we think was, it wasn't probably an asteroid, but maybe the piece of a comet that entered the planet and exploded before reaching the ground. This was in Siberia. Yeah, it was a large explosion in Russia, right? And if you look at the images, you can see the radius of the destruction event, right? So that can be considered as a dangerous approach. All right. It's still not very clear because it was in 1908. So clearly we don't have video or pictures of the event itself. But some people have described it as an object that looked like this. So that's why some astronomers believe that it was probably a very small comet, or at least part of a comet that entered the atmosphere and survived the disintegration, right? The friction of the atmosphere, and then exploded before reaching the ground. And as it says here, it was about 5 to 50, right? Megatons. So much stronger than the Hiroshima atom bomb, right? That's why it's considered one of those exceptions that happened more than 100 years ago, but still, right? But if we disregard that, we can say that the closest approach of a comet in the solar system that eventually crash, and crash in quotation because you know it doesn't have a surface, but went into Jupiter is a Shoemaker-Levy. This was in 1992. Yeah, I remember. I read this in the magazine about this comet that a lot of people were scared about because crashed into Jupiter, and some people didn't really know what was going to be the effects, right? It's a gas giant. So we know there was some perturbations in the atmosphere. You see the impact size in there? So it left some evidences of the encounter. But because Jupiter doesn't have a surface, it's per se, you can only see the effects of the comet on the upper atmosphere, right? Because of the strong gravitational pull and magnetic field of the planet, most likely the comet, which was already disintegrating, by the way, as it approached Jupiter, it didn't probably even reach the interior of Jupiter before disappearing, before all these parts disappearing. Okay? Also take into account that comets are mostly made of ice, so they can easily fragment, just like the Hayakutake as well. As the Hayakutake passed by the Earth and then approached the sun, the comet started to disintegrate. Okay? Again, that is not necessarily what happened with asteroids, because asteroids are mostly made of rock and metal. For example, some meteorites that we have found, we see a large composition of iron. Some iron meteorites, mostly made of iron and nickel, right? And the thing is that those are very nice to be, those are easy and nice to be found because they don't disintegrate in the atmosphere as easily as a rocky asteroid, right? The erosion won't be affected, right? They won't be easily eroded like rocky, like stony meteorites. For example, this. All right. So let's show you what can happen if an asteroid impacts the planet. So that's the difference, right? Even if it's a small asteroid, right? Chances are that if one of those impacts the Earth, this was in 2013, because of the large amount of energy as it enters the planet, it can cause some small destruction. For example, look at the damaged buildings in there. Or for example, this one, right, in the car there, right? Or this one also in Russia, right? A lot of this happen in the northern hemisphere, by the way. And this has to do with the way that meteor, in this case, the asteroid, enters the planet. And because some of these iron meteorites, they can be deflected by the magnetic field of the planet. So then they are deflected towards the north. That's why, right? So that's one way to put it. Remember that the north magnetic field of the planet is located in the south. Okay, so the north magnetic field is on the southern hemisphere and the south magnetic field is on the northern hemisphere. So a magnetic field goes from north to south. So if you follow the magnetic field lines, it makes sense that we find a lot of the meteorites in the northern hemisphere. Now, the last dangerous impact that happened by possibly an asteroid was the one that happened 65 million years ago at the end of the Cretaceous, right? So in the late Cretaceous, you see swamps and rivers, right? But 65 million years ago, there was this impact, right? We have found evidence of this in the Yucatan Peninsula in Mexico, right? If you ever go to Mexico, guys, you probably are gonna go to these caves. These caves that look like this. Those are underground caves or underground rivers, right? And the reason they have these caves all over the Yucatan and the Riviera Maya, right, is because when the comet or the asteroid, right, impacted the Earth, a whole bunch of material was ejected from the Earth. And as the material rained down the Earth, it started to melt a lot of the regions surrounding the impact crater. That's how those caves were formed. And you can actually see it, because I was in one of those, and yes, you can see the formation. This is millions years old caves. And you can see how the geography changed because of the impact, All right? It's actually very nice. Something very nice that you guys should do one day. So all of this dust and material eventually cover the planet. After 40 minutes, this is what happens. So of course, it covers the sun. So what do you have if you don't have sunlight? You have sort of like an ice age. So all the life that was in the planet, all the rivers, the plants, the dinosaurs, they start to die because of lack of sunlight. Then oxygen is also going to be, the amount of oxygen is going to be affected. In fact, guys, the composition of the planet changed so much that the atmosphere changed. Maybe you don't know this, and I was reading about this last year. The percentage of nitrogen in the atmosphere has decreased. It was higher back then. And because of this, insects were actually bigger. So a lot of people that don't really wonder, right? If you have watched Jurassic Park, they show the picture of the mosquito inside amber. And a lot of people tend to be like, okay, but then you see the mosquito, It's quite big. Why don't we have larger mosquitoes anymore? Or per se, larger reptiles, like, 65 million years ago? That's because the amount of nitrogen and oxygen have changed because of this. This event triggered a change in the atmosphere. So this type of ecosystem didn't come back as it was 65 million years ago, right? The environment readapted to the new atmosphere. And eventually we had flowers, plants, and mammals that started to evolve. Now, be careful with that misconception. During this time, we already had some mammals living and probably escaping from the dinosaurs. But this is the thing though. Because of climate change that was already happening before the impact of the comet, some mammals rely to eat dinosaur eggs. And this was told by me by a paleontologist. So the extinction of the dinosaurs was already happening as before the comet struck the planet because of two factors. Mammals were evolving and eating dinosaur eggs, and climate change was affecting dinosaurs the most because the mammals that existed were small enough to hide in caves. And many of them survived after the impact of the comet. After the comet impact and change the geography and geology of the planet, look after 10 years and then after 50 years. So after 50 years, all the dinosaurs were extincted. And then we have other animals, other type of trees. That's why the botany changed. If you ask a botanist or a paleontologist about the landscape of the Earth 70 million years ago, they will tell you how different it was to what it is right now. Again, because the atmosphere and the geology of the Earth changed because of this event. Which is why, if you think about it, we are always worried about what can happen to the Earth and what may have happened to Mars. Because another theory, one of the theories of what happened to Mars, right, why it became inhospitable for life, is that probably an impact of a comet or an asteroid triggered a massive extinction level event where, in which Mars was never able to recover. In the case of the Earth, it recovered because it has a strong gravitational pull to keep an atmosphere, and because regardless of the impact of this large body, water never went away. You see, it didn't dry all the water on the surface, right? You can still see water 10 years and even 5 years after the impact. And that's key for the evolution of life. If water has dried, then the picture of the Earth may be a bit different. Okay? So the Earth has survived this extinction level event. Now, according to Earth scientists, people who investigate the history of our planet from 4.4, 4.3 billion years ago when it was formed to now, we have endured 4 to 5 extinction level events. The first two, however, were when life was not fully evolved. In fact, one of them is still believed to be due to a gamma ray burst. There's not really an evidence for that, but some scientists believe that billions of years ago, before the dinosaurs, okay, a supernova or a gamma ray burst approached the planet, wiping the wiping whatever life was evolving by then. Okay. The latest one will be this, right? The Ice Age is not really considered an extinction level event because Ice Ages are natural cyclic processes, right? Which, by the way, we may have another one, we don't know, not in the next 100, maybe in the next 1,000 years. We are not sure what triggers that. It can be a combination of what happens here on Earth and what's happening with the sun, you know, sunspots, solar activity. Okay. Regardless, it's always important to investigate what happened throughout our planet's history and how our planet has evolved from that, right? Now, we humans are kind of a more reliable species, right? We rely a lot in technology, but should an event like this happen, then it makes sense for NASA and other space agencies to prepare, you know, to prepare the planet for any, for that event, right? The first thing we should do is how to predict when it could happen, then how to avoid it. For example, the DART project, right? I don't know if you guys have heard about it, but NASA, a couple of years or last year, launched a spaceship towards an asteroid in the asteroid belt to analyze how much we were able to deflect this asteroid. And the idea of this DART project, right, is to see how much energy we actually need to actually move this object out of orbit. The idea will be to do the same if an asteroid, for example, was in its approach to the planet, right? I'm going to assume that many of you have watched movies like Deep Impact and Armageddon, right, in the late 90s. Classic movies, but very, very, with a lot of misconceptions. I mean, the idea of landing on an asteroid has been done by NASA, by the Japanese Space Agency, by the Chinese, even the European Space Agency. That we can do, right? We have done that to explore asteroids, right? And I think I explained this before. We explore asteroids because they contain all the history of the formation of the solar system. What's fiction, unfortunately, is to be able to walk on an asteroid and drill, right? Asteroids have such low gravitational pull that nothing will be able to actually stay and walk on the asteroid, right? The other issue is actually drilling, right? I just told you that we have found meteorites that are rich on iron and nickel. Well, good luck trying to drill there, right? So no, unfortunately, that wouldn't work. Launching nuclear bombs also doesn't work. And actually, those movies explain it very well. If you launch a nuclear bomb or a nuclear missile towards an asteroid, you have to take into consideration that there is no gravity in space. So the way the explosion will happen won't be as it happens here on Earth, right? Because there's no atmosphere. So it will be very different. And if it happened, it will just cover the surface. It won't be strong enough to deflect it, right? The idea of using lasers and solar panels has also been proposed to deflect asteroids, but we will have to have a large distance between us and the asteroid. So that doesn't necessarily will help if the asteroid is too close, which is why the DART project seems to be the one that NASA and other countries are actually aiming for, right? So, well, now to prepare for the worst case scenario, we have the idea of having bases or having life moving to planets like Mars or having bases on the moon, right? For the eventuality that we might actually need to colonize those planets, right? It's not as easy as you may think, though. The amount of money and the complications of going to another planet, right? We're still kind of scratching the surface, but it's always good to have these several proposals, several ideas in hand, right? What else we have here? So that's basically it about comets and asteroids, guys. So again, the main difference between comets and asteroids is their composition and where they are coming from. Comets have two sources, the Kuiper belt and the Oort cloud. Asteroids are coming from the orbits between Mars and Jupiter. And the composition, as I said, asteroids are mostly made of rock and metal, while comets are mostly made of ice and some rock. By the way, guys, talking about meteor showers, there is going to be one in December. There you are. In fact, there's one next week, the Geminis. So there you are. So you can actually try and watch it. I don't know if you can watch it from here. Take a look at it. The Leonids happening in November and the Taurids as well. So you can always take a look at this. It's online. All right. And some of those have quite a few good amount of hourly rates. So there's the amount of objects you can see per hour. Okay. Why do we call them, for example, the Geminis? Because you have to look towards the Gemini constellation. All right. So the Ursa Minor is always above the horizon, guys. So there you are. So take your time, guys, before Christmas. December 22nd is on a Sunday. So there you are. You can actually go with family and see if you can watch it. All right. Hopefully it won't be rainy though. So you can actually have a clear skies. Okay. All right. So that's the end of the solar system, guys. But of course, since we talk about the solar system, let's talk a little bit about the sun. All right.